Welcome back, Pre-Calc. We're working on 2.3, finding zeros. Also talking about the type of graphs that we're looking at, the end behavior, and something else. And I'm going to probably give away a few things without you examining them. But they tell you f of x is a cubic. One note to point out here is that can be verified by the number of zeros that you see. Now, I do need to be careful with how I say this because I can give you an example of a cubic that only has one zero. I just draw right here and I'll erase it. This is an example of a cubic that only has one zero, but if I were to shift this, it would cross the x-axis twice, or sorry, 3 times. Well, it would be moved, but I think you get my point. So that's why they go ahead and tell you. Now, if you look at the left end behavior, I kind of want you to get in the habit of writing it this way. When I talk about end behavior, I like to say with arrows and infinity symbols. So as x goes infinitely to the left, because remember, x is left and right, then we talk about the function f of x. And this time, remember f of x is y, so that's up or down. Well, if we look at it to the left, as x goes to the left, this function is going down, so that would be negative infinity. And then the right end behavior is going to be the opposite of that. As x goes to positive infinity, that is to the right. You don't have to write a positive symbol to say you're going to the right. This time the function is going up. And that direction is positive infinity. So to the right, this function is going up. Now my picture is already super messy. And then the zeros, as we look at where it crosses the x-axis, we usually write it in order: -2, -1, and 1. Now looking at the next one, let me just switch colors for you. This time they tell you it's a quartic. That's a to the 4th power. In case you didn't know, quart is a prefix for 4. There's 4 quarts in a gallon. There's 4 quarters in a football, basketball game. 4 quarters make $1. There's a reason why we say that. So as we look at this one, as x goes to negative infinity for the end behavior, this time the function, is named g, is going up. So that's positive infinity. The right end behavior, as x goes to positive infinity, this time the function is also going up. And then the zeros, well, if you notice, there's a few unique things here. Now, I remember this graph from the previous one. It was -2.5 or -5/2 if you prefer writing it that way. And then this 0 is a wonky 0. It goes through the x-axis, but it goes at this weird, cubic-like thing. I'm going to give this away to you. This is your indicator that it has a multiplicity. So this one has a multiplicity of 3. Because it kind of goes through there as a multiplicity. All right. And then we have one more graph to examine. Let's just go with black, boring black. This time it's a quintic. That's how I pronounce it, but we won't get into the pronunciation of things. As x goes to negative infinity, you can see it's going back down. H of x is going down. So it looks a lot like the cubic, the f function. As x goes to positive infinity, it's also going up, again, just like the cubic. And this time the zeros, as I'm examining, where it crosses the x-axis, definitely crosses at -4. It does not cross at a wonky thing. Same with -2, it just crosses. Now at +2, it definitely does something weird. Kind of like a quadratic, a parabola. It just goes up and touches that axis. That's also a clue for a multiplicity. And I also want to mention x equals 5, it looks like, if I'm reading the graph correctly. Now that x equals 2 having a multiplicity, you know how I mentioned it's sort of like a quadratic, a parabola? that's your clue that it's an even multiplicity, in this case a multiplicity of 2. So what does it mean to be a multiplicity? Multiplicity is basically how many times if we're talking about like the form x minus a is a factor. And the clue that you're looking for is in the exponent. So I'm going to write m for multiplicity as your exponent. Because if it's a multiplicity of 2, the exponent would be 2. So like this example, let me go back to blue since I wrote it, would have been x minus 2 cubed to have a multiplicity of 3. While I'm at it, I'll also mention that this is actually called a point of inflection as well when it has a multiplicity of 3. We'll get a lot more deeper into that when we get into calculus. This one is not a point of inflection, but I kind of hesitate to mention that. But anyway, so this one, it would be written in the form x minus 2 in order to get the 0 to be 2, but then squared to have a multiplicity of 2. And hopefully that's making sense. Okay, so I think we're ready for the next page. Actually, let me just go to the answer key to talk about this one. Please don't forget that you can pause the video at any point. You can go back, rewatch whatever you need to, or you can try it on your own and then see what happens. So what you should notice about this is the sum of the multiplicity of the zeros and the degree of the function should be equal. Okay, so the number of roots that you have, number of zeros that you have, should add up to the degree of the polynomial. That's a fundamental theorem of algebra. So the behavior of the graph as it approaches 0, whose multiplicity is 1, is it just goes straight through, does not change what's called concavity. In part 3, if it has a multiplicity of 2, it just touches the x-axis. The word used here is tangent. That's tangent to the x-axis. You probably remember that word from geometry. It means it just touches at one place. It does not go through. Bounces back. And then if it has a multiplicity of 3, it has that point of inflection, and in calculus we call that changing concavity. So it goes from an upwards U to a downwards U. Let me go back a page and just show you real quick, and then I'll come back. So you might want to hit pause if you're still writing. So back a page. You see how it goes from a downwards U and changes to an upwards U. And it could go the other way as well, an upwards U to a downwards U. And that is called a point of inflection, and that's indicated by changing concavity, when you change the U shape. And let's go back to the notes, see how far we can get. All right. So on our next one, how do we know that x plus 1 is a factor? Well, because its root is x equals negative 1. So we can test the multiplicity, even though I already told you it has just a multiplicity of 1. It should make sense that it just has a multiplicity of 1. 1, 2, negative 1, negative 2. And synthetic. 2, 0. And if I try to do this one more time, so I'm just going to switch colors, what you'll notice, sorry, it's kind of good on the next page, it doesn't give me a factor, a remainder of 0. So this was a waste of time. So x equals negative 1 is only a factor once. It has a multiplicity of 1. Now that should have also been obvious, because if the sum of the zeros really equals 3, well, you can see the other two right there. So it's impossible for this one to have a multiplicity larger than 1. But what happens, what's the behavior of the graph, is it crosses the x-axis without changing concavity. All right, I'm feeling good here. If we look at this next problem, x minus 1, that's the root, x equals 1. So maybe I'll do my work over here so I don't go into this answer. 2, negative 1, negative 4, 3. We'll make a conjecture. What do you think is going to happen before we do this? You know, is it crossing the x-axis? Is it just bouncing? If it's bouncing, what kind of multiplicity is it? Is it crossing with change in concavity, like an upwards U to a downwards U, or something else? And then test it. Well, if you do your synthetic, you know, adding and multiplying. Okay, so it definitely happens at least once. Let's see if it happens again. Bring the 2 down. Add, multiply, add. Okay, so there's twice. Let's try it a third time. If you try it a third time, didn't get a remainder of 0. So that third time did not work, did not count. So its multiplicity is 2. And how do we know? You know, at x equals 0, or sorry, at x equals 1, it bounces off the graph, bounces off the x-axis. I mean, that's not a good calculus phrase. That's why the person that made the answer keys wrote, you know, it's tangent to the x-axis. But we're just going to leave it as bounces off or just touches. I had one student say kisses the x-axis, but you don't have to use that phrase here. And that should make sense because there's only one other 0 here, and it's right here. And remember, the sum of the multiplicities has to equal 3. Well, this has a multiplicity of 1. This has to have a multiplicity of 2 to add to be 3. So let's see if we can get the next one. Maybe you're making a conjecture already about the multiplicity at x equals 1. So looking at x equals 1, does it go straight through? Does it bounce? Does it go through and change concavity? And then let's double check on negative 1, 1, 3, 2. Definitely works once. Definitely works twice. And let me just change colors because this last one will not work. I don't think I give you any problems where you have a multiplicity more than 3. And if I do, then I'm sorry, I just lied to you. So this multiplicity is 3. How do we know? It crosses the x-axis and changes concavity. Sometimes I might give the answer, because you know me, there's always more than one way to write this. Sometimes I might write out crosses the x-axis at a point of inflection. You know, something like that is also acceptable if you want a different way of saying the same thing. All right, so I'm going to stop the video here. We'll catch you up to finish these notes in the next video.